Hi there, welcome to this video. My name's John, and in this video we're going to take a look at a problem that I've selected from a mathematics admissions test. So it's the 2018 MAT that we're going to be taking a look at, and it's question number 6 from that paper that we're going to take a look at. So I wouldn't necessarily typically go for this question Hi there, welcome to this video. My name's John. In this video we're going to take a look at a problem from a mathematics admissions test from the 2018 MAT test, and it's question number 6 that we're going to take a look at. So let's jump straight into it today. So this is one of the more structured problems from the MAT. So those of you that are familiar with the MAT will know that the first question is typically multiple choice, a series of multiple choice problems. And then from question 2 onwards, you get much more structured problems where you've got to work much harder. So this problem actually it's not specifically for mathematics applicants. This is for computer science, mathematics and computer science and philosophy. Nevertheless, if you are applying to a university to do mathematics and you need to do the MAT, don't be afraid of looking at when you're doing your preparations and you're going through past papers and things like that. Don't be afraid of looking at some of the problems that are not specifically for mathematics students, because some of them are still quite good quite good practice. And question number 6 from this paper is something that is definitely the kind of thing that you would be expected to do anyway as a mathematics applicant. So even though in this particular year, this particular problem wasn't specifically for mathematics applicants, I don't see any reason why it couldn't have been. There's nothing in there that would suggest that it's not suitable for applicants of mathematics. Okay, so let's have a look at the problem then. So as usual, I will put the problem up on the screen at various times throughout the video so that you can see the problem yourself. I will leave a link in the description to the video so that you can download the paper and you can have a look at this problem and some of the other problems from this paper and the other past papers as well. So let's get into it then. So a positive rational number q is expressed in friendly form if it is written as a finite sum of reciprocals of distinct positive integers. For example, 4/5 is equal to a half plus a quarter plus 1/20. So straight off the bat, you're introduced to something that you probably haven't come across before. Okay, this friendly form, as they call it here, is I've never come across this before, or that term before. I've come across the concepts before of expressing a fraction as a finite sum of reciprocals of distinct positive integers, but I've never heard it called friendly form before, and this is deliberate, so that you're being given a new concept effectively. You're having a concept that you haven't seen before defined to you, and you have to take it and you have to run with it. Okay, this is the whole point. So it shouldn't put you off if you haven't come across this term friendly form before. Then it shouldn't be something that really concerns you, because I haven't come across it before either. Okay, so part 1 then. Express the following numbers in friendly form. Okay, so as is typical with an MAT problem, you kind of eased into the problem before you get to the hard work. Okay, so initially you might not have much of an idea about how to deal with this friendly form of a rational number. You might not have a systematic way of going about finding it. None of that matters. I didn't either. Okay, just do your best. And possibly as you go through these three rational numbers here that we're expected to express in friendly form, you might start to see some patterns. You might not. Okay, either way, it doesn't make any difference. It's not gonna prevent you from going on to the next few parts anyway. Okay, so for the first one, 2/3. To express this in friendly form, I didn't really have to do much work for this one. It just seemed kind of obvious to me that this is equal to 1/2 plus 1/6. Okay, it's just one of those things that I knew. I knew that 2/3 is equal to 1/2 plus 1/6. So there wasn't really any method there that I could give you. Okay, for the next one, 2/5. So with this one, what I personally did was I thought about certain equivalent fractions, fractions that might be equivalent to this. So, for example, 4/10 and 6/15, for example, and 8/20 was one that caught my eye, and for some reason I decided to focus in on 8/20. Okay, so 8/20. These are all equivalent fractions, by the way. For one reason or another, I decided to concentrate on 8/20. And after a little bit of playing around, I think what I did was, because I didn't write everything down that I did. I try not to, so that there's some things, as I make these videos, there's some things that I've still got to think quite carefully as I'm making these videos. So you might notice that in some of the videos that I make, I do actually still make mistakes, even though I've got my kind of a rough solution already written out. I've still missed a lot of the details out, and I still do make mistakes in the videos, but I leave them in because that's part of the problem-solving process. So I think what I did here was I thought, I wrote out this list: 1/20, 2/20, 4/20. And the reason that I'm writing these out is because 1/20 is equal. These are all equivalent to reciprocals of distinct positive integers. So 1/20, we've got 2/20, which is of course is equal to 1/10. 4/20, which of course is equal to 1/5. Whereas if I'd written in here 3/20, this doesn't cancel down. Okay. This is not equal to the reciprocal of a positive integer, so I'd leave that one out. So basically what I'm looking for here is something over 20 where the numerator is a factor of the denominator. So 5/20, 10/20, and of course 20/20. Now I'm probably not going to be interested in 20/20, so I can kind of get rid of that one. And then what I do is I find a way. I look at the numerators, right? The denominators are all 20. What I'm looking at is how can I make the number 8? How can I add these numbers? And I can only use each number once. So I've got 1, 2, 4, 5, and 10. How can I add these numbers together to make 8? Not necessarily all of the numbers. Okay, so some selection of the numbers. How can I do that? Well, obviously 10/20 is no good. So we've got, of course, 1 plus 2 plus 5. 1 plus 2 plus 5 is equal to 8. So that tells me then that 2/5 is going to be equal to 1/20 plus 2/20 plus 5/20, which is equal to 1/20 plus 1/10 plus 1/4. And that gives me a friendly form for 2/5. Now, interestingly, the friendly form of a fraction is not unique. So, if on the other hand I had decided to focus on 6/15, and don't ask me why it was 8/20 I decided to focus on, it just was. I don't know why. But let me now think about 6/15. So let's have a look. 1/15, we can have 3/15, 5/15, and of course 15/15. Let me have a look at the numerators of each of these, and is there any way that I can add a selection of these numbers together in such a way as to get 6 in this case? Well, yes, there is. 1 plus 5 is equal to 6. So the upshot is that 2/5 is also equal to 1/15 plus 5/15, or better written as 1/15 plus 1/3, which is also a friendly form. So what we see here is that the friendly forms of rational numbers are not unique. Okay, so there might be different possibilities that you can go for. So it doesn't matter which one you go for. So I've gone for my answer here. The first answer that I arrived at was the 1/20 plus 1/10 plus a quarter, and then I just decided to have a little play around with the idea, as you should do, by the way. If you're not actually in your MAT exam, do not treat it like an MAT exam. Okay? If you think that there's something more to a particular problem, something that's worth investigating, investigate it. You've got the time to do it, and it's worth your time. Obviously not in the exam, but as you're doing your preparation, play around with the ideas, experiment a little bit. Don't just answer the question and then just move on. Think about things, because this is where you will learn a lot of stuff, by playing around with these ideas. If you're just churning out the solutions to problems, but you're not really taking the time to think about stuff, you're not going to be learning as much as you think. Okay, and then finally, what have we got? 23/40. So I did a similar thing here, except I didn't bother thinking about any equivalent fractions here. I just went straight in, just on the off chance that it worked. So I thought about 1/40, 2/40, 4/40, 5/40, 8/40, 10/40. Hopefully I don't miss any out. 20/40 and 40/40. Again, all of these will cancel down to a form which is 1 over n, where n is some positive integer. Okay, that's why I'm specifically choosing these fractions. Now, you might think, well, this takes a lot of time to write all of these out. It doesn't really take that much time. If it does take you, if you do struggle to find the factors of a number like 40 or something like that, and something's not right. But you've got to do what you've got to do. If you think that this is too long, the solution that I'm presenting here is too long, too laborious, or whatever, then I urge you to find your own better solution. And this is not, I'm not trying to say that in a sarcastic sort of sense, as if you can't do it. It's a genuine invitation for you to use your imagination and do something better, find something better. That's certainly what I would have done when I was doing my A-level maths and further maths. If I wasn't happy with a solution to something, try to find a better solution. Sometimes you do, a lot of the time you don't, because you come to realize why the solution is being presented in the way that it is. and you realise that the solution has been written by somebody that's much more knowledgeable than you at that moment in time. But every now and again you do come across something that you think, I actually prefer this rather than that. So have a go. Okay, so again, is there a way that I can add the numbers in these numerators together, some selection of these numbers together to get 23? And the answer to that is yes. 1, 2, and of course 20. So 23 over 40 is equal to 1 over 40 plus 2 over 40 plus 20 over 40, which is equal to 1 over 40 plus 1 over 20 plus 1/2. Okay, so as I was saying right at the start, even if initially you haven't kind of got a systematic way of dealing with these, there might not be one. There might not be a systematic way of solving a particular category of problem. But sometimes there is, and sometimes you might come across it. So I feel that I have a fairly systematic way of finding a friendly form, as it's called, a friendly form of a positive rational number. Okay. So let's have a look at part number 2. So this was quite a challenge to do as part 2. As with a lot of problems, the difficulty is just finding the right way to view the problem. Okay, but nevertheless, a problem is, to me, something that doesn't have a routine solution to it, where you've really got to think creatively, you've got to think originally, and you have to find that right track. And this is what you're going to be tested on. In your MAT, are you able to just try things out, to not get disheartened when you try something and it doesn't work? Or do you actually understand what a problem is in the first place? Because a lot of people, this might not apply so much to MAT candidates, but a lot of A-level maths students, they really don't get the concept of problem. Everything to them is like a question, something that has a routine solution. And when they're presented with something that they're not familiar with, their initial reaction is to say, I've not been shown how to do this type of problem. Okay? And that's the whole point. That's what you're being tested on. Can you take something that you're not familiar with and just go with it? Okay? Be sure to express your ideas in your MAT. Even if you don't find a solution to the problem, express some ideas, because this will count for something. It doesn't all come down to whether you get the answer or not. Whether you get the tick because you get the right answer. That's only part of what you're going to be assessed on. Okay, so let Q be a rational number with 0 less than Q less than 1. And M is, this is important, really important, let M be the smallest natural number such that 1 over M is less than or equal to Q. And suppose Q is equal to A over B, and Q minus 1 over M is equal to C over D. In their lowest terms, show that C is less than A. Okay, show that C is less than A. So this is what we want to prove. So, okay. So I did a few things, and you've just got to be prepared to try things out. And some of the things that you do won't work. Some of the things that you do, you'll realise when you'll do something and you'll realise actually you've just gone all around the houses to do something that was actually really straightforward. I'll give you an example. So what I did originally when I set about this, I looked at q minus 1 over m. So q is equal to a over b. So we've got a over b minus 1 over m. And we know that this is equal to c over d. Okay, so I got a common denominator here. And I got am minus b over bm is equal to c over d. And then I multiplied through to get rid of the denominators, to clear denominators. So I got amb minus bd is equal to cbm or whatever. So then, because b and d are positive integers, then a and b minus bd is going to be less than a and b. So I concluded that a and b is greater than cbm. Cancel through by m because m is also a positive integer. And I get ab is greater than cb. Sorry, I should have been AMD. AMD, shouldn't it? AD is greater than CB. And I didn't really feel that this was going anywhere. It's really not, because I could have deduced this right from here. The fact that AD is greater than CB, I could have just deduced it straight away from here, because A over B is going to be greater than C over D, and therefore AD is greater than BC or CB, whatever. And you notice things like this, okay? You do something, you think, oh, this seems like a good idea, I'll give it a try, and 2 or 3 minutes later, you realise that you've done something. You've taken 2 or 3 minutes to do something that you could have done in 5 seconds. But this, you cannot avoid this. Okay, you mustn't use the possibility that this could happen. Should not discourage you from trying things out. You might, at the end of it, feel foolish. So when I did all of this, I felt a little bit foolish. I thought, well, you know, I've just spent all of this time figuring something out that I could have figured out in, you know, in a line or two. But that's how it is, okay? And it's things like this that you will continually learn from. But that learning process never stops. Okay? You never eliminate the possibility of doing trying an idea that just doesn't work. And if my take on this is that if everything you do works first time every time, you're doing something wrong. And I don't mean that you're the problem that you're trying to solve, that it's an incorrect solution. I mean the problems that you're trying are not problems. They're not challenging enough for you. Okay, that's what you're doing wrong. If you're just managing to get everything right first time every time. Okay, so I did try a few other things out, which I'm not going to go through absolutely everything that I tried out. I did try, so we know that, for example, 1 over m is less than or equal to q. So I tried to do a bit of case analysis. I said, okay, well, if 1 over m is equal to q, what happens? And if 1 over m is less than q, what happens? Well, if 1 over m is equal to q, then what we get is that a over b minus 1 over m is going to be equal to 0, which is equal to 0 over d. Remember, a over b minus 1 over m is equal to c over d. So c is equal to 0, which is clearly less than a, and hence a is greater than c. So that's, I thought there might be something here, there might be something worth pursuing here, but once I tried 1 over m is less than q, I couldn't really think of anything that was going to take me any further. I did try out some specific cases. So the from part A, the fractions that the rational numbers that we've already expressed in friendly form, I decided to have a look at those in a bit more detail. So I looked at 2/3. So remember, 2/3 was equal to a half minus a sixth. So 2/3 minus a half is equal to 1/6. Okay. Now it turns out that m equals 2 is the smallest positive integer for which 1 over m is less than or equal to q, which in this case is 2/3. And yes, surely enough, we get c, which is equal to 1 in this case, is less than 2, which is equal to a. So yeah, it's verified there. So what about the 2/5? And I do recommend that you do things like this. Because this might be the thing that kind of generates an idea for you. By looking at these specific cases, you may pick up on a certain pattern that you can generalize. So the whole point of these videos is not for me to just give you a model solution, it's to give you ideas about things that you can try out yourself. Even though some of those things won't necessarily work here for this problem, they might work for other problems. Okay, so I'm keen to not just show you the way to solve this problem. If that's what you're here for, this is the wrong video for you. Okay, so what do we have? 2/5 minus a quarter. Now there's a problem here. Okay, we've got 2/5 minus a quarter is equal to, what is it? It turns out to be 3/20. Okay. Now, have a look at this. Here we've got c, which is equal to 3. Okay. But a is equal to 2, right? This is a, and this is c. But, c is greater than a here. What's the problem? The problem is this thing. Okay. 4 is not the smallest positive integer such that 1 over m is less than or equal to q. It's actually a third. 3. So 2/5 minus 1/3, okay, is equal to, try a half. 2/5 is less than a half, but 2/5 is greater than a third. Okay, and it turns out that this is equal to 1/15. Aha. Okay, so we get here c equals 1, a is equal to 2. And again, we get that c is less than a. Okay, so you've got to be really careful. And it's, again, doing stuff like this draws your attention to why this bit of information is important. And what this highlights to me is that the fact that m is the smallest natural number such that 1 over m is less than or equal to q, this must play a role in my solution. Because notice that I've not actually used that yet anywhere. It's conspicuously absent from anything that I've tried as of yet. The fact that that m is the smallest natural number such that 1 over m is less than or equal to q, I have not used that yet. And that's probably part of the problem. If you're trying to solve a problem and you're struggling to find a solution, and there's a bit of information that you've been given that you haven't incorporated into your solution, that's probably why you're not able to find a solution. Okay, even when you try to incorporate that bit of information, it might not be easy to do so, but you've got no chance of solving that problem without using that bit of information. So my attention then turned more towards that bit of information. How can I incorporate that bit of information into my solution? Okay, so I did try another couple of things out, none of which really worked. It probably took me about 10-15 minutes to arrive at something that worked here. Oh, let me give myself a bit more space. Okay, so my solution was as follows. I know that 1 over m is less than or equal to Q, which equals A over B. I also know that A over B is less than 1 over M minus 1. Okay, so here, this is an expression of that bit of information. Right, a symbolic expression of that bit of information, that the smallest natural number, M is the smallest natural number such that 1 over M is less than or equal to Q. And sometimes this is the difficult part, actually finding a suitable way to express that bit of information in a way that you're actually going to be able to use it in your calculations. Here it turned out not to be too difficult, but sometimes it can be really difficult to do. So, okay, I've already had a play around with the 1 over M less than or equal to A over B. So now I'm going to have a look at this A over B less than 1 over M minus 1. So, M has to be, because Q is between 0, remember, 0 less than Q less than 1, that means that if that 1 over 1 is always going to be greater than Q. Okay? So, M minus 1 is going to be greater than or equal to 1, and therefore M is going to be greater than or equal to 2. Okay? Again, little bits of information like this really make all of the difference sometimes. Just write these things out. These little observations that you make, they're worth writing down in your exam. This is the kind of thing that your examiners will be looking for. Above and beyond, just, did you get the solution or not? What did you see? Were you seeing some sensible and useful things? Were you trying to pursue ideas? Even if you weren't fully able to execute those ideas, to fully follow through on them, were you able to at least make a start with something? Were you making clever observations? Okay, so 1 over M minus 1 minus A over B, therefore, is going to be greater than 0. So we don't need to worry about negative numbers and things like that here. So we can multiply through, clear denominators, and I get B minus A M minus 1 is greater than 0. Therefore, B minus AM. Now, don't do the silly thing and write B minus AM plus 1 is greater than 0, which I did originally. These little slips do happen from time to time, and it left me scratching my head for about 5 minutes. So make sure that when you expand your brackets out, you do it properly. Lesson learned. Okay, and that tells me then that A is greater than AM minus B. Okay, so that's as far as I seem to be able to take that. Okay, and I had no idea, I honestly had no idea whether this was actually going to be of any use to me whatsoever. But again, you've just got to go with the flow. Just pursue ideas and see what happens. Okay, so then, if I just scroll down a little bit, give myself a bit more space. So then I went back to A over B, what is it? A over B minus 1 over M, or Q minus 1 over M. So A over B minus 1 over M equals C over D, or so we're told. Again, I can multiply through, clear denominators. Or actually, no, not clear denominators. I can get a common, on the left-hand side, get a common denominator. So I get MA minus B over BM is equal to C over D. Now I started to think this could be useful to me. Because look, AM minus B, MA minus B. Same expression. Okay, it's written in a slightly different form, but it's the same expression, right? AM minus B, MA minus B. So I still wasn't necessarily totally convinced at this point, but I was becoming more convinced. So I decided to use that and write that A over BM is equal to C over D. Okay, so sorry, not equal to, is greater than. Beg your pardon. Okay, so remember C over D. Little bit of information that we're told about C over D. What was it? It's in its lowest terms. Okay. These little bits of information that you're given, they're so important. Really pay attention to them. C over D is in its lowest terms. It doesn't cancel down any further. However, A over BM may or may not be in its lowest terms. So may not be in lowest terms. Okay, so yeah, okay, so because of the equality that this inequality is derived from, okay, so I'm talking about this inequality, this equality here. This would suggest if these two fractions are going to be equal or equivalent, that means that BM has to be some constant, some positive integer constant multiple of D. Okay, so BM must be equal to K times D. Okay, where K is an integer and it's greater than or equal to 1. Okay, so that means that I can replace the BM here, this BM, with KD. So I get A over KD is greater than C over D. So I can cancel through by D. D is a positive integer, so I can cancel it. It's not 0 or anything like that. So I get that A is greater than K times C. But remember, K is greater than or equal to 1. So K times C is greater than or equal to C. Hence, A is greater than C. Exactly what I needed. Okay? So it really... I really do want to emphasize again just how important these little bits of information are that you're given. And how important it is that when you're given a bit of information, that you really make sure that you try to incorporate that bit of information into your solution at some point. It's very, very rare for you to have a problem that has superfluous information. It does happen, it can happen, but these problems are typically very well thought through, and the information that you're given is necessary and sufficient for you to solve that problem. Okay, so you don't need any more information, and you can't have any less information, any fewer bits of information to solve that problem. Okay, so bear that in mind. So part 3, what was part 3? Suggest a procedure by which any rational q with 0 less than q less than 1 can be expressed in friendly form. Use the result in part 2 to show that the procedure always works, generating distinct reciprocals and finishing within a finite time. Okay, so let's start with q equals A1 over B1. Okay, and choose M1 to be minimal, the smallest natural number. So I'll just say minimal, just because I can't be bothered writing everything out. Choose M1 minimal so that 1 over M1 is less than or equal to A1 over B1. And calculate A1 over B1 minus 1 over M1 and set this equal to A2 over B2. Okay, and we know that A2 is less than A1. This is going to be really important, by the way. So now, again, choose M2. And again, I'll say minimal, which means the smallest natural number in this context. Minimal. So that 1 over M2 is less than or equal to A2 over B2. And then A3 over B3 is, you guessed it, A2 over B2 minus 1 over M2. And we have that A3 is less than A2 is less than A1. And notice that it's less than, not less than or equal to. And this is what is going to allow us to show that this always works, and and it finishes within a finite time. Okay, it's this strict sequence of inequalities. If it was less than or equal to this, then we wouldn't necessarily be able to deduce, not using this particular approach that I'm taking here anyway. So we just continue that, okay? So continue, and you don't need to be perfect here. You just need to make it clear how your method is working. Okay, if you want to write out a general kind of form, so in general, you might have something like an over bn is equal to a n minus 1 over bn minus 1 minus 1 over m n minus 1, where m sub n minus 1 is minimal, whatever. Fine, do this, but don't worry if you don't get everything absolutely spot on perfect. Again, it's the ideas. Show your examiner your ideas. That's what they're interested in. So what we get in general is that a n is less than a n minus 1 is less than a n minus 2 is less than a2 is less than a1. Okay, so a1 is a finite number, is a finite positive integer. Suppose A1 is equal to uppercase M. Okay. Then after, at most, M steps, N iterations of this, AN will be equal, AM will be equal to 0. Okay. And once you've got to that, you've got to a point where 1 over a whatever it is, an is equal to, a over this 1 over m that we're using is equal to, maybe I shouldn't have used uppercase M, it's too late now. 1 over m is equal to a n over bn or whatever. Okay, that's the point at which you would terminate. So what we see then is that we've got a procedure here that's based around the results from part 2. We just keep iterating that until we get to a point where so in part 2 we were looking for the smallest natural number such that 1 over m is less than or equal to q. Once we get to a point where we've got 1 over m is equal to q, that's when we stop. Okay, that's when we can stop. We don't need to go any further. Okay, so I've given a bit of an idea there. I'm not saying that how I've written it out there is exactly how I would have written it out in an exam. I think it could do with some more clarification, but I'm going to leave that up to you to find your own way of expressing yourself for that. I've given you the idea. Okay. Oh, it's raining. Okay, so demonstrate your procedure by finding a friendly form for 4/13. Okay, so we know what to do. You have got to hunt around a little bit here. So, for example, a half. I figured out that half is greater than 4/13. I figured out that a third is greater than 4/13. Okay, so third, get a common denominator here. What's it going to be? 39. A third is equal to 13/39. 4/13 is going to be 12/39. So we get that a third is clearly greater than 4/13. But once we get to a quarter is equal to 13/52. Whereas on the other hand, 4/13 is equal to what do I need to multiply by? 16. That's it. 16/52, which is smaller than. So the smallest natural number whose reciprocal is less than 4/13 is 4. Okay, and yes, you do just have to hunt around. So then we do 4/13 minus a quarter. Just do it, and it turns out to be 3/52. Okay, 3/52s, and then we've got to do the same thing for 3/52. Notice that our C here is less than our A, which is as it should be. Okay, so then what did I try? I tried a series of numbers actually. I started with 1/13. So I found that 1/13, comparing this with 3/52. What do I get? Multiply by 4. Yeah, okay, so that's 4/52, which is greater than 3/52. So 1/13 is not the 13 is not the number that I'm looking for. I tried 1/14. 1/14 and 3/52. It turns out that 1/14 is equal to. I'm not doing all of this again, if I can help it. 14 times 26. It's equal to 26 over something. And 3/52. What did I do? 14 times 22. I don't know. Right, anyway, it turns out to be greater than. Can't be bothered figuring it all out now. But do these. You have to do these calculator. And yes, you have to do these without a calculator. And I did do these without a calculator. I tried 1/15. Turns out that this is still greater than 3/52. And I continued until I got to 1/18. Turns out that 1/18 is less than 3/52. So 18 is the smallest natural number such that its reciprocal is less than 3/52. So then what do? It's 3/52 minus 1/18. Okay, 3/52 minus 1/18. Think about maybe prime factor decompositions if you need to. So for example, 52 is 2 times 2 times 13. 18 is 2 times 3 times 3. This will be useful in a few minutes. Not so much now necessarily, but it will come useful in a few minutes. These decompositions, and what I get is I don't know. What do I get? Oh, it's 2/52 times 18 which is 1 over 52 times 9. 52 times 9 is 520 minus 52. 1 over 468. So what was it? 4 over 13. So 4 over 13 is equal to a quarter plus 1/18 plus 1 over 468. Okay, and that's a friendly form. And the reason why these prime decompositions might be useful is if you want to check this. And I do recommend that you do this. So 4 is 2 times 2, 18 is 2 times 3 times 3. 468, where did we get that from? 52 times 9. Okay, so this is going to be 13 times 3 times 13 times 6. 12 times 6, 72. Hang on. If I made a mistake somewhere. Hope not. 13 times 3. 39. Times 3 again. 39 times 3 is 117. Right, okay, yeah. 117 plus 2 times 3 multiplied by 26 plus 2 plus 1 over 468. 118 plus 26, 130, 144. Which is 72 over 234. 36 over 117. What does that cancel down to? Yeah, it cancels down by 9. 4 over 13. Now, of course, I don't need to check if I don't want to. But I chose to. I chose to check. Okay. If you don't want to check, don't check. Right. So, finally then, assuming that the sum from n equals 1 to uppercase n is equal of 1 over n increases without bound. We'll come back to that in a second because I don't like assumptions. As n becomes large, show that every positive rational number can be expressed in friendly form. Okay. So let's say q is a rational number. Okay, then since the sum from n equals 1 to n of 1 over n increases without bound. Without bound. This means that there will be an n such that the sum from n equals 1 to n of 1 over n is less than or equal to q, but q is less than the sum from n equals 1 to n plus 1 of 1 over n. Okay. So if we've got equality, then we are done. Why? Because the sum of 1 over n is 1 plus a half plus a third plus a quarter plus it's a finite sum of reciprocals of distinct positive integers. Okay, so it's in exactly the right form. It's a friendly form. By the way, this way of expressing rational numbers in this friendly form, it kind of resembles the way that ancient Egyptians used to represent their fractions. They typically worked with what we now recognize as reciprocals of distinct of positive integers. Sorry. So they didn't have things like 4/5 or 7/11 and things like that. Although they did have 2/3. Interestingly. Anyway, beside the point. So, if on the other hand we have n equals 1 to n of 1 over n is less than q, then we have that q minus this sum is less than, and remember, bear in mind this, what I'm doing is effectively subtracting from the q and from this sum here the sum from n equals 1 to uppercase n of 1 over n. So when I do that, what am I going to be left with? I'm just going to be left with 1 over n plus 1. Okay, which is less than 1. And also, we've got 0 over here. 0 is less than this. So in other words, this is a rational number between 0 and 1. Okay, in the interval 0, 1. So we're in exactly the case now from part 2. Almost. Because in part 2, notice that for something to be written in a friendly form, it's got to be written as a finite sum of reciprocals of distinct positive integers. We've already knocked some out, right? We've already knocked out the expressions 1 over 1, 1 over 2, 1 over 3, 1 over 4, up to 1 over n. Okay? But this is fine, actually. This is fine. Because the rational number that we're interested in, that's in this interval 0 to 1 is less than 1 over n plus 1. So the smallest natural number that we can find now, such that, so the smallest natural number m, such that 1 over m is less than or equal to q minus the sum from n equals 1 and 1 over n. So this smallest natural number is going to be greater than or equal to n plus 1. I think it's probably going to be greater than or equal to n plus 2. Doesn't make any difference. So, as we hunt for this smallest natural number, we're not going to have to worry about all of these expressions, these reciprocals of natural numbers that we've already got accounted for. We don't even need to look there. So we apply the procedure that we outlined in 3. So apply procedure outlined in 3 to get a friendly form for q minus the sum from n equals 1 to n of 1 over n. And therefore q is going to be equal to this friendly form, so this new friendly form, plus the sum from n equals 1 to n of 1 over n, which is a friendly form. This is a friendly form, this is a friendly form, and because there's no there are no reciprocals that occur in that are kind of that occur more than once, then the whole thing is a friendly form. Again, I'm kind of giving the outline idea here rather than writing everything out. I'll leave it up to you to write out your own solution to this. Okay, but that brings us to the end of this particular problem. Now, we were told at the start of part 5 here, assuming that this sum increases without bound as n becomes large. We don't need to assume that. I mean, okay, we can do because we're told to, but we don't need to. Let's actually look at this bonus material. Okay, bonus material. So this sum is 1 plus a half plus a third plus a quarter plus a fifth plus a sixth. There is a reason why I'm writing out this much of it. Plus 1/10 plus and so on. Okay, so we're going to group these together in a particular way. Right? So I'm going to group these on their own. I'm going to group these 2 terms together. I'm going to group these 4 terms together. And then I would group the next 8 terms. And then the next 16 terms. And then the next 32 terms. Why? Why would I do this? Okay. So, let's in each of these groups, let's have a look at the final number that occurs. So in this case, we've got it's 1 over 2 squared. Here it's 1 over 2 cubed. Here, just for sake of completeness, it's 1 over 2 to the power of 1. Kind of forget about the 1. It's a bit of a... It doesn't really fit the pattern, but it doesn't really make too much difference. The end of the next group, where we've got these 8 terms, the final number would be 1/16. That's 1 over 2 to the power of 4. How many terms is in each group? Here we've got 4 terms, or 2 squared. Here we've got 2 terms, or 2 to the power of 1. Here we've got 8 terms, sorry, 2 cubed. So notice that each of these sums, so if we take this sum a third plus a quarter, this is greater than a quarter plus a quarter, which is equal to 2 to the power of 1. Remember, there's 2 to the power of 1 terms, 2 terms, times 1 over 2 squared, which is a half. For the next lot, a fifth plus a sixth plus a seventh plus an eighth is greater than an eighth plus an eighth plus an eighth plus an eighth, which is equal to 2 squared terms in that group, times 1 over 2 cubed, which is a half. You see where this is going? Each of these groups, the sum of the terms in each of these groups is greater than a half. So what we end up with is that the sum from n equals 1, n of 1 over n. So this is going to approach, as n gets large, 1 plus a half. Sorry, it's going to be greater than. It's going to be greater than. This is not really very good notation, but it's going to be greater than 1 plus a half, plus a half, plus a half. However many halves you want to add on, which approaches infinity. Okay. So in other words, we can prove that this sum will diverge. It will diverge to infinity. And by the way, if you try to use a computer to show this, you'd have no chance. You need to use logic. I mean, actual proper logic that's suitable for doing the kinds of pure mathematics that we're talking about here. Computers wouldn't be able to discern. Even if you had a really powerful computer, it wouldn't be able to tell you that this sum would increase without bound. Try it, but you won't have any luck. Okay, so that brings us to the end of this problem. So it went on a little bit longer than I expected, but there was some interesting stuff there. If there is anything you want to ask, if there's anything that you're not clear about with this problem that I've said in this video, I'm sure there are many things, feel free to ask about them in the comments section. If you've got any ideas for problems, anything that you'd like me to cover, let me know. Please show your support for this channel by hitting the subscribe button, hitting the like button. I don't make any money from these videos. I do them because I want to do them, and I want to pass on some of my knowledge to help you prepare for your MAT and STEP exams, or A-level maths and further maths exams. But if there is anything that you think I could be doing better, let me know. At the minute, I'm just kind of making the videos. It's a very small channel. I've only got a few subscribers, and therefore I'm kind of making the videos for myself more than anything. But I'd rather be making the videos for other people so that I can help them. So let me know if there's anything that you think I could be doing better, if you've got any ideas about anything. But on that note, I think the video's gone on long enough. And thank you for watching. Congratulations if you made it this far. If you are preparing for your MAT exams, I wish you the best of luck. And I hope that you are deriving some benefit from watching these videos. Thanks for watching, and I'll see you in the next video.